Hello friends, good morning. In my last class, I had explained the differential relays. These are the relays which operate when phasor difference of two similar electrical quantities exceeds certain predetermined value. So normally we connect instantaneous relay in differential circuit and it acts as differential relay. So again, I will take the reference of same diagram. This is the protected zone. It can be transmission line, distribution line, transformer, generator, motor, or bus bar. These are two cities. In between these two cities, whatever equipment we are using, that is protected, and that is it is unique type of protection because it is not providing protection to for the faults outside the protected zone. It is not acting as backup protection. So these are city secondaries. Dot mark shows current leaving. So through this relay, current is I1 minus I2. That is relay current. This I had explained in my previous lecture. For differential relays, the faults outside the protected zone are called as true fault. Now let us see the reasons why the relay operates for the true faults. Here I will define one important term, that is true fault stability. It is the ability of the differential relay to remain inoperative for the true faults, to remain stable for the true faults. So when relay operates for the true fault, we say that the relay has lost the true fault stability. Means it is operating for the fault outside the protected zone. Now there are three reasons for such type of operation. There are three reasons why the relay loses the true fault stability. Number one is unequal pilot wire resistances. Second, unequal CT ratio. And third is CT saturation. Let's take one by one. First is unequal pilot wire resistances. Now here, when we are connecting the instantaneous relay in differential circuit, the requirement is it should be connected at the equipotential point so that during normal condition, current through this relay should be zero. But if we are not connecting this at equipotential point, means the pilot wire resistances are not equal, then some current is flowing through this relay during normal condition also. This current will proportionately increase when there is true fault. Whenever there is fault, this current will proportionately increase. For internal fault, there is no problem because relay has to operate. But for external fault, when this current increases and it exceeds the pickup value of the relay, then the relay operates. The first reason for loss of true fault stability is unequal pilot wire resistance. Second reason is unequal CT ratio. So here I will take simple example. This is CT1 having ratio of 100:1. CT2 should have same ratio, but due to some manufacturing defect, it may have 100:0.99 ratio. This is almost equal to 1, but very small minute difference is there, that is of 0.01. Now let us say load current. In normal condition, load current is flowing through CT1 and CT2. 100 amperes load current is flowing. So it is 100. Secondary current will be 1 ampere. It is 100. Secondary current will be 0.99 ampere. So IR, that is relay current, I1 minus I2 will be 1 minus 0.99. That is 0.01 ampere current is flowing through the relay in normal condition. Let us say pickup is 0.1 ampere. Now current is 0.01 ampere, pickup is 0.1 ampere, so relay will not operate during normal condition. Now let us consider external fault condition. Now during external fault, current may exceed up to 20 times. So during healthy condition, current was 100 amperes. Now let us say current has become 2000 ampere during the external fault condition. So secondary current will also proportionately increase. So for 100 it is 1, for 2000 it will be 20. But this will not be 20. It will be 19.8 amperes. Here it is 20, it is 19.8 amperes. So current flowing through the relay is I1 minus I2, that is 0.2 ampere. And it is greater than the pickup of the relay. So for this true fault, the relay is going to operate. This relay is losing its true fault stability. And it is happening due to unequal CT ratio. Ideally, we should have identical ratio, but due to manufacturing defect, the cities practically do not have exactly identical ratio. So even when some small difference is there, it will become fatal when it is external fault. Third case is city saturation. City saturates means it stops contributing the proportionate current on the secondary side. Now let us say this GT2 gets saturated at 1000 ampere. Fault current is 2000 ampere. GT1 is not saturating. So it is contributing 2000 ampere. Here it will be 20 ampere. But if this saturates at 1000 ampere, the proportionate current on the secondary side will be only 10 ampere. So IR, that is I1 minus I2, will be 20 minus 10, that is 10 amperes. So that is more than the pickup of the relay. So relay will operate. So these are the reasons for causing the maloperation of the relay, or alternatively we can say these are the reasons due to which the relay loses its through fault stability. In the next class, I will explain how these drawbacks are overcome, means how we avoid the maloperation of the relay for external faults. Thank you.